All right, this morning what I want to do is take some time, let me turn the light on, and we're going to look at positive sequences and sums of positive terms. And as we do this, what I want to do is I want to talk about when and how you use certain things. I know when you're doing tests and you do one test at a time, it always seems like, oh, this is easy. It's easy as long as you're just doing one test at a time. But as soon as you get to where it's, hey, does it just converge? And you have to come up with the why, then it becomes a lot harder. Okay. Now, the first test that we're going to talk about, they've changed its name. Now, when I say they've changed its name, when I was a kid, they called it something else. Okay, the first test that we're going to talk about is the Nth Term Test. Today, they're calling it the test for divergence. And it says this: if you have a series, oh, and by the way, the terms are positive for all n, it will diverge if, when you take the limit of the general term, regardless of the index, it's not 0. Okay? So consider this. Okay, I'm going to sum this on k. It doesn't matter. Obviously, a sub k is positive for all terms. Okay. In fact, we're starting at 2, so it doesn't matter. But when I take the limit as k goes to infinity of the general term, that's the limit as k goes to infinity. And then I rewrite the general term down. Now, there's a lot of people that get L'Hopital's happy here. You don't need this. In this case, just look at this. This is a ratio of polynomials in terms of k. The degrees are the same, therefore the limit is the ratio of the leading terms. Since the limit is not 0, it diverges. Therefore, by the nth term test, or the test for divergence, the series k equals 2 to infinity of the rational expression k squared over k squared minus 2k plus 5 diverges. Now, I want you to hit pause. I want you to copy this down. And I want you to do this one. Now, okay. Now you should have done it. So here's what you're going to do. You're going to take the limit as n goes to infinity of the general term. And now I'm going to use substitution. The limit as n goes to infinity, and I'm going to replace a sub n with its general term. Now, I'm going to do this in steps. We know that y equals the natural log of x is a continuous function as long as x is greater than 0. So I'm going to use my theorem, which allows me to rewrite this as the natural log of the limit as n goes to infinity of this rational expression. Okay. Now that rational expression, the degrees of the numerator and denominator are the same, so therefore it has a limit, which is the ratio of the leading coefficients, which is 1/2, which is not 0. And now I can grab the conclusion. Therefore, and I'll use their words this time. Therefore, by the test for divergence, also known as the nth term test, the series, and you rewrite the series out, don't just say the series. You never know, because sometimes they can get really picky with words, and it's just better to be safe. Diverges. Okay. Now another type of positive series, sum of positive sequence, is a telescoping one. Now telescoping ones are unique. The most basic case is you can think of most telescoping series as this difference of two harmonic series. Now by themselves, harmonic series diverge. But when you subtract some harmonic series, they telescope. So we're going to go back, and our first step is going to be to decompose these. Okay. I'm going to multiply both sides by n times n plus 3. When I do that, I'll have 3. The denominators will all simplify out on the other side. The n simplifies, so I get an n plus 3. If n is negative 3, this will be bn. So if n is negative 3, that's 0, and I get negative 3n is 3, so b is minus 1. If n is 0, I get 3a is 3, a is 1. So I can rewrite this as 1 over n minus 1 over n plus 3. And as soon as I see that subtraction, I know that there's hope that I can get this to telescope. So now I'm going to look at the first partial sum. That's 1 minus a fourth. And I'm not going to actually figure it out. 2. So that'll be 1 minus a fourth. And I'll have a half minus a fifth. So far nothing's simplifying out. So third, 1 minus a fourth. And a half minus a fifth. Now let's put 3 in there. Now we're going to have a third minus a sixth. So for the fourth partial sum, this will be 1 minus a fourth plus a half minus a fifth plus a third. Now I'm going to put in the last term, and now I start to see something happening. A fourth minus a seventh. The fourths simplify out. On the fifth partial sum, I'm going to have all of this, but then I'm going to have a fifth. So I'm going to have 1 plus a half minus a fifth plus a third minus a sixth minus a seventh, and then I'm going to go plus a fifth minus an eighth, and the fifths simplify out. For the sixth partial sum, okay, I'm going to have 1 plus a half plus a third minus a sixth minus a seventh minus an eighth, and now I'm going to go plus 1/6 minus 1/9. Okay. Now notice, on the seventh partial sum, the 1/7 will simplify out. So this is always going to be there. I think 6th. So 6 plus 3 is 2 over 6 minus plus 3 s sub n. That'll be, let's see, 11/6 minus 1 over plus 3. Now, I take this limit. So, as n goes to infinity, this sum goes to 11/6 minus nothing. So it's approaching 11/6. So the sum is 11/6. But now notice, I had to write out 6 or 7 partial sums to see that that happened. Now let's take a look at this one. This one caught my eye and I said, wow, this is kind of interesting. This is different. E to the 1 over n minus e to the 1 over n plus 1. Okay, s sub 1. E minus e to the 1/2, s sub 2. E minus e to the 1/2 plus e to the 1/2 minus e to the 1/3. Oh, look, the e to the 1/2 simplify out. S sub 3. E minus e to the 1/3 plus e to the 1/3 minus e to the 1/4. Simplify, simplify. So notice what's happening. I'm always keeping this. So the nth partial sum will be e minus, and then I'm subtracting this. So the limit as n tends to infinity of the nth partial sum, this is e minus nothing, which is e. So this series is approaching the irrational number e. Another basic positive series is the harmonic series. And I'm just going to bring this up real quickly. We'll prove this when I get to the improper integral test. I call it the improper integral test. The books call it the integral test. This diverges. Now, if you remember in class, what we did was we started adding terms and we were grouping things and adding halves. And we just kept slowly, we'd add more and more terms till we kept getting more and more halves. And this goes on forever, so this diverges. Then we have geometric series. And that says, now you can either write it this way, or you can write it this way, depending on where you want to start your series from. Okay? Converges. The series converges, not the sequence. If the magnitude of the common ratio is a proper fraction, and if it is, then your sum will be the first term over 1 minus the common ratio. So let's say I gave you this series. Okay, I'd say, hey, look, the absolute value of the common ratio is a fourth. That's a proper fraction, so it converges. And it converges to 1/4, which is 12 over 3/4, which is 48/3, which is 16. Okay, then from there we went to the next granddaddy, the integral test. The integral test uses improper integrals. It's very, very important. And it says that the improper integral and the infinite series will either both converge or they will both diverge. Now, books do it differently, so you have to pay attention. So, the way books now are doing it, because see, my book was different. They talked about the series and then having a function model. Well, now they say, suppose you have a function f that's continuous, it's positive, and it's decreasing when you go from 1 to infinity, and it matches up with the sequence. A sub n is f sub n. Then the series converges if the improper integral converges. The series diverges if the improper integral diverges. So let's look at the harmonic series. In fact, I could start that at 2 if I really wanted to. Okay. F of x, 1 over x, f is positive, clearly, if x is, f of x is positive if x is an element of 1 to infinity. It's continuous, because you're not dividing by 0 on that interval. Okay. It's a function model. f prime of x is minus 1 over x squared, and that obviously is negative if x is greater than or equal to 1. Why? If you square a positive number, it's positive, and if you divide a positive number into negative 1, it's negative. I have now satisfied, oh, hold on, I need to finish this. So this says f is decreasing on 1 to infinity. Therefore, we've satisfied the hypothesis of the integral test. Now we're going to apply the integral test. And what I like about this is now we're doing some review. So this is the limit as b goes to infinity of the integral from 1 to b of 1 over x dx, which is the limit as b goes to infinity of the natural log of x using the fundamental theorem, which is the limit as b goes to infinity of ln b minus ln 1. The natural log of 1 is 0, but as b grows without bound, the natural log of b grows without bound. Now, what does this tell me? Now, right now, I'm only talking about the improper integral. Hence, the improper integral from 1 to infinity of d over x, dx over x diverges by the integral test, the integral from, or not the integral, the series from 1 to infinity of 1 over n also diverges because they do the same thing. Okay? Now, the integral test is used to prove the p-series test. So anytime you see a p-series, that's the summation from k equals 1 to infinity of 1 over n to the k to the, wait a minute, I'm writing this wrong, p. Yeah, let's just rewrite this, Mr. Isaac, wake up. And now look, you don't have to start this at 1. It could start at 2, 3, 4, whatever. Converges if p is greater than 1. It diverges if p is bigger than 0, but 1 or less. So if you see a series, let's see, like we have this one, we'll do it in n. N goes from 4 to infinity of 1 over n to the point 1. So this is a divergent p-series. Why? Because p is a tenth, and a tenth is less than or equal to 1. Why? If I integrate that using the antiderivative of a power series, and I add 1 to the power negative a tenth, I'm going to get n to the 9/10 times 10 ninths. And when I take that limit as n goes to, or as b goes to infinity for that upper limit of integration, it's going to be growth without bound. That's the y. Now from there we can estimate the sums of the series like we talked about in class. And then finally, I wanted to keep this to be less than 20 minutes, but it's not going to happen. We had the comparison test. There are two comparison tests. There is the direct comparison test, and there's the limit comparison test. What both of them tell you to do before we talk about what you need to show is you both are going to compare these series that you have to something you know something about. And then you're going to be able to, based on what you know something about, if you show certain things, say that they both converged together or they both diverged together. Piece of cake. Now, this one, the limit comparison test, is far more forgiving because you only have to take the limit. And if the limit is a finite number, you're done. You can move on and say what you need to say. Now, I'm going to do this problem twice. I'm going to use both comparison tests on it. I'm going to start with the direct comparison test. Okay, so first of all, when I look at this, for n very, very large, adding 6 here really doesn't matter. So I'm going to compare this to now you should be able to see in your head that when I do this, it is a convergent infinite geometric series because the common ratio is 1/4. The magnitude of the common ratio is 1/4, which is a proper fraction. Converges because it is an infinite geometric series where the magnitude of r is 1/4, which is, I don't care what it converges to, I just know it converges. Now, for the direct comparison test, what I want to know is this. I want to be able to bound this. So is 4 to the n always going to be less than that same power, but I add 6, and that's always positive. So when I take the reciprocal, what's going to happen is I'm going to have this. This is true for all n. I've just shown that this term, general term of the positive series that I'm interested in, is bounded by this general term. So what's that mean, Mr. Isaac? If I add these up, that means that this series is dominated, its partial sums, term by term, in our case, for all n, 4 to the n. And since this dominates it and this converges, this forces this to converge by the direct comparison test, the series 1/4 to the n plus 6, where n goes from 1 to infinity, converges. Now notice you had to do some inequality work there, which can be tedious. Now, this problem with the limit comparison test, look at how much more forgiving this is. I'm going to compare it to the same function. So I form the ratio of a sub n to b sub n. This is what I want to compare it, what I want to determine. So now in my head I can see this. If I clean this up, I get 4 to the n over 4 to the n plus 6. I'm going to factor out a 4 to the n of the numerator and in the denominator and simplify them. Okay, so the limit as n goes to infinity of a sub n over b sub n is the limit as n goes to infinity of 1 over 1 plus 6 over 4 to the n, which is, okay, this numerator has a limit of 1. This right here goes to 0. And 1 plus 0 is 1, and 1 over 1 is 1. So I look at this limit. This limit is finite. Therefore, they're growing at the same rate. Therefore, they both converge because the one I compared it to converged by the limit comparison test, the series n equals 1 to infinity of 1/4 to the n plus 6 converges. Let me know if this helps. I'll do more. Time for football.